Good morning everyone, myself Muskan from BSc Chemistry Honors first year. Today I read a chapter of Organic Chemistry by Dr. J.M. Sehgal, chapter named Aryl Halides. Introduction. Aryl halides are aromatic halogen compound in which the halogen is directly attached to aromatic ring. They are assigned the general formula ARX, where AR is a phenyl, a substituted phenyl, or some other aryl group such as naphthyl. For example, we have chlorobenzene, orthobromotoluene, metabromotoluene, etc. It may be pointed out that the term aryl halide does not include aromatic halogen compound containing the halogen in the side chain such as benzyl chloride. The latter type of compound, often referred as to aralkyl halide, are in fact only aryl substituted alkyl halide. Aryl halide need separate treatment because they differ widely from aryl halide, including aralkyl halide, in their methods or preparation and properties. Nomenclature. Aryl halides are named by adding appropriate prefix of the halogen chloro, bromo, or iodo and its position if necessary to the name of the parent aromatic compound as illustrated below. Bromobenzene. Methods of preparation. Aryl halide generally prepared by the following methods. Number 1. Nuclear halogenation. Aryl chlorides and bromides can be conveniently prepared by the direct chlorination or bromination of aromatic ring. The reaction is generally carried out at low temperature in the absence of sunlight and the presence of Lewis acids such as ferric halides and aluminium halide, which act as catalyst. The catalyst is generally known as halogen carrier. The usual practice is to add the reaction mixture some iron fillings which are converted by the halogen into the corresponding ferric halides, which acts as the Lewis acid. For example, chlorobenzene is obtained when benzene is treated with chlorine in equimolar quantities in the presence of ferric chloride. 2Fe plus 3Cl2 2FeCl3 बनाएंगे. Halogenation normally stops at the monosubstitution stage, but if halogen is used in excess, a second halogen gets introduced mainly into ortho and para position with respect to the first. For example, क्लोरोबेंजीन के साथ Cl2 एक्सेस में डालेंगे तो ऑर्थो और पैरा डाइक्लोरोबेंजीन मिलेगा. Similarly, toluene may be chlorinated as or brominated in the presence of iron at low temperature, the reaction taking place more readily than in case of benzene. Limitations of nuclear halogenations. As a precipitative method, nuclear halogenations suffer from the following limitations. Number 1. In many cases, nuclear halogenations yield mixture of isomeric aryl halide, which may be not easily satisfied. Number 2. It is not always keeping to prepare aryl halide with specific orientation of substituent. For instance, metabromotoluene can't be prepared by the direct bromination of toluene because methyl group is ortho and para directing. Number 3. Aryl iodides can't be prepared unless the reaction is carried out in the presence of oxidizing agents like nitric acid and mercuric oxide. This is because iodination is a reversible reaction and oxidizing agents are needed to shift the process in the forward direction. Aryl fluorides are never prepared by this method because the reaction with fluorine is very violent. It must be emphasized, however, that in spite of the above limitations, direct halogenation of aromatic compound is a useful method for the preparation of aryl halides. This is in a sharp contrast to the direct halogenation of alkanes, which direct halogenation of alkane which is seldom employed for the preparation of alkyl halide due to the formation of complex mixture of products. Number 2. From diazonium salt. The decomposition of diazonium salt under suitable conditions is probably the best method of preparing aryl halides. Aryl chloride and bromide are obtained by treating the diazonium salt solution which cuprous chloride is dissolved in HCl or cuprous bromide dissolved in HBr. This reaction is known as Sandmeyer reaction. For example, benzene diazonium chloride से CuCl डाल के chlorobenzene. In place of CuCl or CuBr, it is also possible to use copper powder and HCl or HBr. The reaction is also known as Gattermann reaction. Iodo compound are obtained just by warming the diazonium salt solution with aqueous potassium iodide solution. The diazonium salt used in the above reaction are themselves obtained from aromatic amines by treatment with sodium nitrite and an acid such as HCl at low temperature. Fluoroarenes are prepared by decomposing the corresponding diazonium tetrafluoroborate. By the action of heat, the fluoroborate itself is obtained by the diazotization of a suitable primary amine. The reaction is known as Wald-Simon reaction. Physical properties. The physical properties of haloarenes are similar to those of corresponding alkyl halides. Number 1. Physical state. In general, haloarenes are colorless, oily, liquid or crystalline solid. Number 2. Density and solubility. They are heavier than water and insoluble in it, but they are soluble in organic solvent. The para compound being generally less soluble in a given solvent than the ortho isomer. This fact is often made use of in the separation of ortho and para isomers. Number 3. Melting and boiling point. Number 1 उसमें the melting and boiling point of haloarenes are nearly the same as those of an alkyl halide containing the same number of carbon atom. Number 2. Amongst themselves, the melting and boiling point increase as the size of halogen atom increase. In other words, for the same aryl group, the melting point and boiling point follow the order iodo, bromo, chloro, fluoro. Number 3. For the same halogen, the melting and boiling point increase as the size of the aryl group increases. Number 4. For ortho, meta and para isomer dihalide, the melting point differ very widely while the boiling point show much lesser variation. For instance, the melting point of ortho, meta and para dichlorobenzene are 256, 249 and 325 Kelvin respectively, while their respective boiling point are 453, 446 and 448 Kelvin. Number 4. The para isomer has relatively very high melting point. This is because the para isomer is very symmetrical and fits better in the crystal lattice. Therefore, it requires much more energy to break the crystal lattice. Chemical properties. The chemical behavior of aryl halides is marked by lack of reactivity under ordinary conditions. Unlike alkyl halide, aryl halide undergo nucleophilic substitution only with extreme difficulty except in the presence of suitable substituent. Moreover, the presence of halogens also deactivates the aromatic ring towards electrophilic substitution. The few important reactions which aryl halides do undergo are discussed. Number 1. Nucleophilic aromatic substitution. It has been stated above that simple aryl halide do not undergo nucleophilic substitution under ordinary condition. However, they can do so under strong condition involving the use of high temperature, pressure or very strong nucleophilic reagent. Number 1. Replacement of hydroxyl group. Aryl halide undergo nucleophilic substitution by hydroxyl ion when heated with aqueous sodium hydroxide at about 623 Kelvin and high pressure. Number 2. Replacement of amino group. When an aryl halide is heated with aqueous ammonia in the presence of Cu2O and at high pressure, the halogen atom is replaced by amino group. A similar reaction also takes place when aryl halide is attacked by a very strong base, potassium amide, in liquid ammonia. Number 3. Replacement of cyano group. Alkyl halide react with cuprous cyanide at about 473 Kelvin in the presence of pyridine to undergo replacement of halogen by CN group. Effect, for example, bromobenzene में CuCN डालेंगे cyanobenzene. Effect of substituent on the reactivity of aryl halides toward nucleophilic substitution. The presence of substituents on the benzene ring has a strong influence on the reactivity of aryl halide towards nucleophilic substitution as discussed. Number 1. Effect of electron withdrawing substituent. The presence of electron withdrawing group like NO2, CN, CO, COH and SO3H, particularly when present in ortho and para position with respect to the halogen, activate the aryl halide towards nucleophilic substitution. Thus, para-nitrochlorobenzene forms para-nitrophenol when heated with 15% aqueous sodium hydroxide at 423 Kelvin. 2,4-dinitro-chlorobenzene changes into 2,4-dinitrophenol by heating with aqueous sodium carbonate at 403 Kelvin, while 2,4,6-trinitrochlorobenzene is converted into picric acid merely by warming with water. Number 2. Effect of electron releasing substituent in view of the activating influence of electron withdrawing group, it is not surprising to find that electron releasing groups such as NH2, OH, OR, R, etc. would deactivate the aryl halide towards nucleophilic substitution. It may be recalled that these groups exert just the opposite influence on electrophilic aromatic substitution, electron releasing group having an activating influence and electron withdrawing group having a deactivating influence in that case. However, whether a group acts as activating or deactivating towards nucleophilic or electrophilic aromatic substitution, it exerts its effect mainly at ortho and para position with respect to it. The reason for the low reactivity of aryl halides toward nucleophilic substitution, the mechanism of these reaction, and the effect of various substituents on the reactivity in nucleophilic substitution are discussed. Electrophilic aromatic substitution. Aryl halide undergo the typical electrophilic aromatic substitution reaction, though the halogen have a deactivating influence on the aromatic ring. It may also be recalled that in spite of being deactivators, the halogen are also para directors. Other reactions. In addition to the reaction discussed so far, aryl halides undergo the following reactions. Number 1. Formation of Grignard reagent. Aryl bromide and iodide readily form Grignard reagent in the presence of dry ethyl ether as a solvent. ArX plus Mg. Dry ether की presence में ArMgX. Aryl chloride do not readily undergo this reaction in the presence of dry ether. However, they do form Grignard reagent if dry hydrofurane is used as a solvent. Number 2. Wurtz-Fittig reaction. When an aryl halide is treated with an alkyl halide and sodium metal in the presence of dry ether, the halogen atom of aryl halide is replaced by aryl group. Fittig reaction. If only aryl halide is treated with sodium in presence of dry ether, diaryls are formed. Ullmann biaryl synthesis. When heated with copper powder in a sealed tube, aryl iodide form polynuclear compound. Aryl chloride and bromide undergo this reaction only if they have electron withdrawing group like NO2 in ortho or para position to the halogen. Aryl fluoride do not undergo this reaction at all. Number 4. Reduction. Aryl halides can be reduced with nickel aluminium alloy in the presence of alkali to form corresponding hydrocarbons. Number 5. Oxidation. An oxidation of nuclear halogenation compound which contain a side chain also halogen atom remains intact while the side chain is oxidized to carboxyl group. Relative reactivity of aryl halides with respect to alkyl halide. Reason for low reactivity of aryl halides. This behavior is in sharp contrast to that of alkyl halide, which are highly reactive compounds. Let us now try to see as to why the halogen in aryl halides is rather inert towards nucleophilic substitution. Explain based upon resonance. An aryl halide is a resonance hybrid of various contributing structures such as structure 1 to 5 shown. It is evident, therefore, that the molecule of the aryl halide is resonance stabilized. Moreover, the contribution of structure like 3,5 impart of a partial double bond character to the carbon-halogen bond in the resonance hybrid of the aryl halide. In other words, carbon-halogen bond in aryl halide is stronger than a pure single bond. Thus, in contrast with alkyl halide, aryl halide exists in the form of resonance stabilized molecule in which the halogen is firmly attached to the carbon. As such, the halogen in aryl and can't be easily displaced by nucleophilic reagent. The above interpretation of the low reactivity of aryl halide is also supported by their dipole moment values. For instance, the chlorobenzene has dipole moment of only 1.7 d, while the dipole moment of alkyl chloride are of the order 2 to 2.2 d. This means that aryl halide are much less polar than alkyl halide. This is obviously due to the fact that the contributing structures such as 3,5 of alkyl halide contain a halogen carrying a positive charge. Contribution from such structures tends to oppose the development of negative charge on the halogen arising from the displacement of electron of carbon-halogen bond towards the more electronegative halogen atoms. Even though there is still a net displacement of electron bit towards halogen in aryl halides, it is less than in alkyl halide. This naturally inhibits the displacement of the halogen. Alternative explanation. There is another explanation also for the low reactivity of the aryl halides. The carbon attached to halogen in aryl halide in sp3 hybridized, while that in alkyl halide is sp3 hybridized. Since the effective size of sp2 hybridized carbon is lesser than of sp3 hybridized carbon, the carbon halogen bond in alkyl halide is shorter than in carbon halogen bond in alkyl halide. An idea of the bond length of carbon halogen bond in aryl and alkyl halide may be had from the act that CCl bond length in chlorobenzene is 1.69 angstrom, while in alkyl chloride than in 1.80 angstrom. This interpretation is also in line with the less polar character of alkyl halide. Thus, the low reactivity of aryl halide towards nucleophilic substitution can be attributed to two reasons: delocalization of electron by resonance and attachment of halogen to sp2 hybridized carbon. Comparison of reactivity of nuclear and side chain halogen compound. Reaction of side chain halogen compound. In order to compare the reactivities of nuclear and side chain halogen derivatives, let us first have a look at the reaction of side chain halogen compounds. Side chain halogen derivatives resemble alkyl halide in their chemical behavior and are very reactive in nature. They undergo a number of nucleophilic substitution reaction. Wurtz-Furtick reaction. On treatment of side chain derivative with alkyl halide or other aromatic halogen compound in the presence of sodium and dry ether, the halogen atom is replaced by alkyl or aryl group. Prudhoe-Kraft reaction. Side chain derivative react with aromatic hydrocarbon in the presence of anhydrous aluminum chloride to give higher hydrocarbon. 6. Reduction. Nascent hydrogen from zinc copper couple and alcohol reduces these compounds to yield hydrocarbons. Reaction with manganese. Like nuclear halogen compound, a side chain derivative form Grignard reagent on treatment with dry magnesium powder in dry ether. Oxidation. Action of oxidizing agent result in the oxidation of the side chain, including the halogen atom present in the chain. Mild oxidizing agent like lead nitrate convert the side chain into CHO group, while reagent like nitric acid change into COOH group. Halogenation of side chain. On treatment with halogenation at higher temperature of the in the presence of sunlight and absence of halogen carrier, the side chain gets further halogenated. Reaction of the nucleus. Side chain halogenation compound exhibit the usual electrophilic reaction of benzene. Mechanism of nucleophilic aromatic substitution by molecular displacement mechanism. Two mechanisms have been proposed for nucleophilic aromatic substitution. These are: number 1, addition elimination mechanism by molecular displacement mechanism. Number 2, elimination addition or benzene mechanism. In this section, we will discuss the molecular displacement mechanism, while the benzene mechanism is discussed in section addition elimination mechanism by molecular displacement mechanism. This is generally expected mechanism of nucleophilic aromatic substitution. According to this mechanism, the reaction takes place in two steps as illustrated below. In case of simple aryl halides, step 1, formation of carboanions. Addition of nucleophile. The first step, which is the rate determining step, involving the attack of nucleophile nucleophile on the carbon carrying the halogen to form an intermediate carbanion, which is a resonance hybrid of various structure. During the formation of this carbanion, the hybridization of carbon atom concerned changes from sp2 to sp3 and the aromatic character of benzene ring is destroyed. The carbanion formed is called Meissner-Hammer complex. Step 2, elimination of halide ion. In the second step, the halide ion is expelled from the carbanion to yield the product in which the aromatic system has been regenerated. This mechanism affords an example of nucleophilic substitution in which the attacking nucleophile reagent becomes bonded to the carbon before the halogen leaves. It is important to note that the formation of intermediate carbanion postulated above is not likely to take place under ordinary conditions from simple aryl halides. It operates only in the case of aryl halides containing electron withdrawing ring substituents such as NO2COOH, which stabilize the intermediate carbanion. The above mechanism for nucleophilic aromatic substitution has been recently supported on the basis of element effect, that is the influence of particular element present in a compound on its reactivity in nucleophilic substitution reaction of aryl halide. The nature of halogen has very little influence on the reactivity of an aryl halide. This means that the reactivity of aryl halide towards nucleophilic substitution is independent of the strength of carbon halogen bond. This can be possible only if the rate determining step of the reaction does not involve the cleavage of the carbon halogen bond as postulated in the mechanism given below. Thus, nucleophilic aromatic substitution involves a two-step mechanism in which the rate of reaction is determined not by breaking of carbon halogen bond but by the rate of attachment of attacking nucleophilic reagent to the aromatic ring to form the intermediate carbanion. Influence of substituents on reactivity in nucleophilic aromatic substitution. As readily pointed out, the presence of electron withdrawing groups such as NO2, CN, SO3H, particularly in ortho and para position with respect to the halogen facilities nucleophilic aromatic substitution. On the other hand, the presence of electron releasing groups such as alkyl OH and NH2 has just two opposite effect. Let us now try to justify this observation. The rate determining step in the nucleophilic aromatic substitution by addition elimination mechanism is the attachment of attacking nucleophile to form the carbanion. That is, it is evident therefore that any factor which stabilizes the carbanion will increase its age of formation and thereby increase the overall rate of reaction. On the other hand, factors which destabilize the carbanion will decrease the rate of reaction. Now, carbanion would be stabilized by group with withdraw electron and thus tend to disperse the negative charge of the carbanion. On the other hand, the electron releasing group which insatisfy the negative charge on the carbanion would naturally destabilize these ions. The withdrawal or release of electron may take place through inductive effect or resonance effect or through a combination of two effects. Let us, for instance, consider that each of para-nitrochlorobenzene, chlorobenzene, and para-chlorotoluene is made to undergo a nucleophilic substitution reaction. The relative rates at which the three react would be found to be related to the relative reactivities of intermediate carbanions. The net result of inductive and resonance effect of nitro group is an electron withdrawing effect. Due to its electron withdrawing effect, the nitro group stabilizes the carbanion. As such, it is easier to form the ion 1 from para-chlorobenzene than to form the ion 2 from chlorobenzene. Consequently, para-nitrochlorobenzene undergo nucleophilic substitution more readily than does chlorobenzene. On the other hand, the methyl group destabilizes the carbanion due to its electron releasing inductive effect. Therefore, it is not ordinarily possible to form the ion. Hence, para-chlorotoluene undergo substitution only under drastic conditions. On the other hand, the methyl group influence of substituents on orientation in nucleophilic aromatic substitution. Let us now discuss the orientation in nucleophilic aromatic substitution. What is the reason that electron withdrawing substituents exert a strongly activating influence on the nucleophilic substitution only when present in ortho and para position with respect to the halogen and have much less effect in the meta position. To understand this, let us compare the contributing structure of carbanion formed during the nucleophilic substitution of ortho, para and meta nitrochlorobenzene. It may be noted that carbanion formed in case of ortho and para nitrochlorobenzene are resonance hybrid of 4 structure each. On the other hand, the carbanion resulting from the meta compound is resonance hybrid if only 3 structures, there being no structure analogous to ID 1D or 2D. Moreover, in the case of carbanions resulting from the ortho and para compound, the result 1C and 1,2B respectively, the particular stable because in the structure and negative charge is located on the carbon directly attached to the electron withdrawing group. No such structure is possible for the carbanion formed from meta compound. Thus, the carbanion obtained from ortho and para nitrochlorobenzene should be much more resonance stabilized than the one obtained from meta isomers. As such, ortho and para nitrochlorobenzene undergo nucleophilic substitution much faster than the meta compound. Comparison of aliphatic and aromatic nucleophilic substitution. It would be quite interesting at this stage to compare the SN1 and SN2 mechanism studied earlier, the nucleophilic substitution of alkyl halide, with the nucleophilic addition elimination mechanism which operates in case of nuclear halogen compound. It may be recalled that SN1 mechanism involved the formation of carbanion as the rate determining step, followed by the attachment of nucleophile to the carbocation as depicted below. As such, the SN1 reaction are facilitated by the presence of electron releasing substituents. In the SN2 mechanism, the nucleophilic become attached to the carbon at the same time as the departing group leaves. Accordingly, such reactions are not appreciably influenced by electronic factors. In biomolecular nucleophilic aromatic substitution, the rate determining step involving the formation of a carbanion in which the nucleophile get bonded with to the carbon before the departing group leaves. That is why such substitution is favorable by electron withdrawing substituent. It may be noted that both in the transition state of an SN2 mechanism of alkyl halide and the intermediate carbanion of biomolecular nucleophilic aromatic substitution, the carbon of reaction site is bonded to the attacking as well as departing group, but the transition state of SN2 mechanism contain a pentavalent carbon and thus represent an unstable arrangement corresponding to the top of energy hill in the progress of reaction. On the other hand, the carbanion intermediate is an actual compound containing a tetrahedral carbon and having the negative charge distributed around the ring. The carbanion intermediate itself is, however, formed through a transition. Thus, the carbanion intermediate corresponding to an energy valley, as shown. The SN1 mechanism is not possible for nucleophilic aromatic substitution because the aryl halide has little tendency to ionize due to the partial double bond character of carbon halogen bond. Similarly, the SN2 mechanism is not feasible because the halogen lies in the plane of aromatic ring, such as attacking nucleophile can't approach the aryl halide from the evidence in support of above mechanism. Many experimental observations provide supporting evidence in favor of benzene mechanism as discussed below. Number 1. When labeled chlorobenzene, in which chlorine is attached to C14 isotope, was reacted with amide ion. The resulting amine consisted of a mixture of two types of molecule. In one type of molecule, the amino group was bonded to C14, and in the other type, it was held by an orthocarbon. This is because once the benzene is formed, the NH2 ion is attached itself to either end of the extra bond present in benzene. A similar situation is afforded by many unlabeled aryl halide too, where also the entering group may be get attached at a position ortho to that of the displaced group. For example, when para-chlorotoluene is attached to by NH2 group, the product consists of mixture of para and meta toluenides. Number 2, ortho deuteribromobenzene has been found to be less reactive than bromobenzene. This isotopic effect clearly shows that orthohydrogen is involved in the initial bond cleavage, and this cleavage must be the rate determining step. Number 3, it has been observed the compound that in having two group ortho to halogens such as 2-bromo, 3-methyl anisole do not react at all. This is because there are no available orthohydrogen atom to be eliminated. It has also been observed that certain isomeric aryl halides yield the same product. For instance, both meta-bromoanisole or para-bromoanisole on amination furnish the same product. Formation of same product in both cases can be justified. Benzene intermediate has also been shown to the form in the reaction of certain aryl halides with organolithium compound. The benzene thus formed reacts with further in the presence of water to yield the final product. Thank you.